Okay, so 3-5 is not a kind of mind-bending concept. It's actually a pretty simple, easier concept than what we've been dealing with. It's necessary. We've even seen some of these early on, but the purpose of this section is for us to realize that not always do we have an understanding of what the sample space looks like. If I tell you a deck of cards, I tell you I've got this setup of marbles in a jar, I've got rolling a dice, flipping a coin, you know, you intuitively know those sample spaces, okay? But if I ask you what are the different families that could be made if we have 3 children based on male or female, you might not instantly know what those 8 different families could be, okay? So we might not, per situation, we might not have a very good understanding of a sample space. So tree diagrams and Venn diagrams allow us to develop those sample spaces and also to recognize relationships between them that allow us to determine certain probabilities. So this first question here talks about that. But by definition, it says a special type of graph used to determine the outcomes of a sample space of an experiment. Okay, consists of branches. Push the wrong button. Consists of branches that are labeled with their frequencies or probabilities. And then as we ask probability questions, we can look at those branches and how they intertwine and interconnect to actually determine overall probabilities. Okay. They all start from a single unlabeled point, okay? You can, and we'll draw a couple different one of these today, but this one's going to be kind of vertical, so it's going to kind of fall down. Some of them, I like to draw the ones that go left to right, but this one kind of takes up a lot of space when you draw them vertically, okay? But what we do is we talk about the situations that we're going to have. So this says the following is a tree diagram for a family of 3 children and the probabilities of their gender. Okay, so what we've got going on here is we're going to have one child, it's going to be male or female. And then if we have a male, the second child could be male or female from there, right? And if we had a male, then a male, the third one could be male or female from there, right? Okay, does the fact that my first child was male have any impact on the second child being male? Huh? So I think you're talking like, was it Mendeleev and his, is it Mendeleev? Is it Lev? So you're talking about like that type of stuff, right? Like recessive and dominant genes, like Punnett squares. Okay, that's not what we're talking about here. Okay, so like you have a probability, first child, so the fact that the first one was male has no impact on the second one. Okay, because what he said was that you're crossbreeding 2 different things, right? Okay. Well, what are you talking about? Do you have proof of that? You sure? I don't. All right. So, first child, male or female, right? Okay. Male or female. So, the second child, okay, if the first child was male, second child could be, yeah. So we got the same situation stemming down here for the second child, okay? So after having 2 children, it could have been a male and a male, a male and a female, okay? But if the first child was female, could that second child have been male, female? Okay. Now my question, just with 2 children right now, would a male, female, would that, as a male being the first child, female being the second child, is that different than a female being the first child and a male being a second child? That family's different, right? Okay, so I just want to make sure we understand that. So now if I go to the third child, so I go male, male, what could be my option for the third child? Male, female, right? Okay. If I go male, female, then we go male, female for that third child, right? If we go female, male, could it be then the third child be male? And if we go female, female, the third child could be male or female. Okay? So now that helps us determine our sample space. Okay? Our sample space is going to be this. Okay, I start at the emanating point and I just travel down all the different routes that are going to get me to these last 8 options. Okay, so I go male, male, male. That is one family. Does that make sense? Okay, so I'm going to list that as one of my objects in my sample space. Then we're going to go male, male, female. Okay, then so we went male, 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 female. Now we gotta go male, female, male. So male, female, male. And then we're gonna go male, female, female. Is everybody kind of getting the hang of this? So now going the female branch first. We have female, male, male. We'll have female, male, female. And then we'll have female, female, male. And female, female, female. Okay? So if I ask you at the onset, what are the different families that could be created, would you have, without looking at the tree diagram, would you have known to choose those 8 or come up with those 8? Or would you have had a systematic way of developing those 8 so that something wasn't counted twice or that you didn't leave something out? Okay? That diagram is exhaustive, meaning it will 100% of the time get you all of your sample space. So this is his question is, can you do a permutation? So a permutation is when order matters. So the idea here, does order matter? Does male, male, female, is that different family than male, female, male? It's the same letters, but different order, right? So it is a permutation, so permutation matters. So what we do here is we would say that we're taking, I think the best way to see a permutation is to think about how many things can I choose for child number 1. You have 2 options, right? Okay, how many options do you have for number 2? Second child, I can only have 2 options, right? Male or female. Third option, only 2 things, right? 2 times 2 times 2 is 8. Okay, so that tells me how many people are going to be in my sample space. Okay, so that's a permutation of 3 objects taking 2 at a time. If we go like, that's the kind of notation that we use for a permutation. But it doesn't tell me specifically, though, what each of these items or outcomes in the sample space look like. Does that make sense? It just tells me essentially what my denominator is. So now they can ask questions. Okay, well, what is the likelihood of this family having all males? 1 out of 18, right? Or what's the probability of having all the same gender? That'd be 2 out of 8, correct? Male, 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 and then female, female, female. We add those together. You can go through and say, what's the probability of having maybe at least 2 males? Okay, and we can count those up and put them out at 8. Does that make sense? So now that you understand what the sample space looks like, the probabilities that we can ask that go with that can be found a little bit easier. Okay. Now, if there are, genetic components that maybe lean, so basically what the idea here is, you've got a one half chance of being male or female, right? The next one is 1/2, 1/2, and all these would be 1/2. These probabilities are all going to be the same. So if I ask you what is the probability that your family is male, female, female, it's 1/2 times 1/2 times 1/2, right? Okay? So then we argue what Riley's point was, well, if I had multiple males initially, then laws of genetics maybe say that the next one is more likely to be male, right? So if we're saying that these are dependent, then that probability would be different. Does that make sense? Okay, but we would still take 1/2 times 1/2 times whatever that is. That makes sense to everybody? Okay, so this question here says a litter of kittens available for adoption at the Humane Society has 4 tabby kittens and 5 black kittens. Family comes in and randomly selects 2 kittens without replacement. So right there, that tells me something about my probability here, my events. If it's without replacement, then what kind of events? They're dependent. So my probabilities are going to change as we move through this tree diagram. Okay, it says develop a tree diagram. What's the probability that both kittens both are tabby, and what is the probability that one kitten of each coloring is selected? So develop a tree first. So this one I'm going to draw horizontally. So there's my point that the tree is going to emanate from. And basically what we're doing is selection 1, and we'll have selection 2. Okay, so if I go selection 1, what are my options? If the idea here is that you like randomly go and you with your eyes closed, you pick out a cat. Okay, what are my options that when I close my eyes and pick a cat, what are my 2 options? Tabby and black. Okay. Now here's my question: if I do that, what was the probability that on my first selection I picked a tabby cat? 4 out of 9. So that means 5 out of 9 was the probability that I chose a black one, right? Okay, so we picked that one, we put it aside, keeping our eyes closed, we're going to pick a second one. If I picked a tabby the first time, what could I choose the second time? Could have been a tabby or a black, right? Okay, so let's think about this though. If I chose a tabby the first time and I kept it out, what is the probability of choosing a tabby the second time? 3 out of 8. Okay. So the likely events, or the event that I'm interested in, and the outcome that aligns with that alter, and the sample space alters because we kept one cat out. Okay. What would be the probability if I chose a tabby first? What's the probability that I choose a black the second time? Still have 5 cats that are black, right? So out of 8. But if we chose a black one first, can I still choose a tabby second? What would be the probability of choosing a black one? And then what's this probability here of choosing a tabby on the second one, given that I've already chosen a black one? 4 out of 8. And then does that make choosing a black one on the second choice also 4 out of 8? That kind of makes sense to everybody? Okay. So the families of cats that I could take home, or the types of cats I could take home, I could take home 2 tabbies, tabby. I could take home the first one tabby, second one black. I could take home the first one black, second one tabby, or they could be both black. Okay. Now, here's what I want us to understand. That is maybe the sample space or the grouping of cats that we're going to take home, but because those probabilities were not, they were dependent probabilities, I can't say, well, what's the probability that both chosen are tabby? Is it 1 out of 4? No. Okay? Because these probabilities kind of skew that. So what we have here is the probability of a tabby and a tabby is equal to the probability that the first one was tabby times then the probability that the second one, I'll put subscripts here, that the second one was tabby given the first one was tabby. Does that make sense? And now I write it that way. It's the multiplication rule, but I write it that way because the events I know were dependent. Okay, if they were independent, I would just write probability tabby sub 1 times probability tabby sub 2. Okay? But because we know that they're going to change, what's the probability of tabby sub 1? 4/9, right? Times the probability of tabby 2, given that 1 is already chosen, that'd be going this route, right? So I got 4/9 times 3/8. And that gives me then 12 out of 72, which that reduces to 1/6. There's a 1/6 chance that we go in there, eyes closed, pick 2 cats out, they're both going home tabby. Is that okay? It says, what is the probability that 1 kitten of each coloring is selected? Okay. So that means the probability of let's say the first one being tabby and the second one being black. Okay, so that would be the probability, first one is tabby, times then the probability of the second one being black, given the first one was tabby. Okay, or could it be the probability of black and tabby, which would be the probability the first one was black, times the probability that the second one is tabby, given the first one was black. Does that kind of make sense? What would I do with these two probabilities? Because I said or, I connected them here with or, but what would I do with those two probabilities? I would add those together once I have them compiled. So probability of tabby, first one being tabby, and then black would be 4/9 times 5/8, right? 4/9 times 5/8. Okay. And the second one would be 5/9 times 4/8. Now here's my question. Even though those individual fractions are different, are their products still the same? Yeah. Okay. You still get 20 over 72 for both of them, right? So that's the Coke problem. The last question of the quiz. It was pop. You had okay, so you had flowers. So I think the homework question was a pop question. The test question or quiz question was about flowers. So 40 out of 72 would be that probability, okay? Because the first one could be tabby and the second one black, or the first one black and the second one tabby. Okay. And you reduce that obviously as you see fit. So it's the same. So two kittens of the same color. Okay. Would you guys agree that that would be? So we've already determined the probability that they're both tabby, right? So that was 1/6. What's the probability that they're both black? It'd be 20 out of 72, right? It'd be that stem right there. So what would I do with those two? So if I had, so what do we say? 12/72s was, or 12/72 was when they were both tabby, and then both black would be 20/72. What am I going to do with those values to say that the probability of choosing two kittens of the same color? Is that when I say two kittens of the same color, am I saying that I could have two that are black or two that are tabby? Okay, so when I say or, what am I going to do with those? Add them together. So 32 out of 72. Is that okay? Let's see here. Let's do this example. It says a college reported the following based on their graduation data. Okay, it says 70% of freshmen had attended public schools. 60% of freshmen who attended public schools graduated within 5 years. 80% of other freshmen graduated within 5 years. How many freshmen graduate within 5 years? Develop a tree diagram first. Okay, so says 70% of freshmen attended public schools. Okay, so let's say this row here is public schools. Okay, so we go public. Okay, and non-public. So if 70% attended public, does that make sense that probability is 0.7? What's this probability? 0.3. Okay. Now it says 60% of freshmen who attended public schools graduated within 5 years. So if they went public schools, okay, so that's a given condition. So we know we're looking here at public. 60% did within 5 years. Just write it within 5 years, and then this one not 5 years. Okay. So what if I go public, and then this one should be, what should this probability on this branch be? 0.6, and this should be 0.4. Okay. It says 80% of other freshmen, which would be the non-public, right? Okay, maybe I should have written that as other. But 80% of them graduated within 5 years. So that should be 0.8 there. And not within 5 years, that would be 0.2. Does that make sense, everybody? Okay. So now it says find the probability that public schools, or that they went to public school and graduated within 5 years. Well, keyword here, and, right? Okay. So I'm going to determine probability of public schools times then probability of graduated within 5 years. Okay, so these are our graduation is dependent. These probabilities were dependent on these, right? Okay, whether it went public or not public. So really, what we're going to do here is 0.7 times 0.6 gives me 0.42, and that's what we're looking for then. Public school and graduated within 5 years. Does that kind of make sense to everybody? Okay. Other school and graduated within 5 years. So other would be 0.3. And then we go that 0.8 route. So 0.3 times 0.8 be 0.24. 24% chance. Is that pretty straight? Do you see how? And we could do these problems here like we did last week, just using the formulas. But if you can set it up in a tree diagram, it may be a little bit easier to see the flow of what probabilities that you're actually going to tie together. Is this something we can do? Okay. Tomorrow we'll jump in and talk about Venn diagrams. And then that will get us to chapter 4. So chapter 4, and this is going to be something that we see as we move on through the rest of the year. So this textbook that we're using has a lot of like extraneous things in it. So some distributions that we're going to talk about are like the main distribution for statistics class is the normal distribution. Okay, bell curves, that kind of stuff, right? But this textbook talks about a lot of different types of distributions. Talks about exponential, talks about chi-square, talks about uniform, talks about Poisson, all types of different distributions, okay? And those are fine, those are great, but introductory to statistics at the college level doesn't require us to learn those right now. Okay, if we have time later on, we'll come back and talk about a Poisson distribution and that sort of thing. but our kind of focus is going to be targeted towards the normal distribution, learning everything we need to about the normal distribution. That being said, we're going to skip through some sections of the text. So if you see, we go to chapter 4, and there's actually going to be 3 sections that we talk about in chapter 4, which if we look at the textbook, there's like 7 sections. Chapter 5, there was only 1 section that we'll talk about in chapter 5. Okay, chapter 6, I think there's 2 sections. Chapter 7, there's going to be 1. Chapter 8, there's going to be 3. Okay, so we're going to, as you are preparing for, and I'll get the notes up on Schoology soon. I've got them all the way written through chapter 8. I will get those up. So if you're preparing, if you're a person that prints off before class, don't just print chapter 5 and think, well, we'll be on chapter 5 for 2-3 weeks. Okay, because chapter 5 will be like a day. Okay, and then we'll get into chapter 6. So those are just some things to look out for. My plan is to, next week, Monday, I hate giving tests on Monday, but that's what we're going to do, because it's even worse to give it on a Tuesday before Thanksgiving and half the people don't show up. Okay, so Monday will be an exam to whatever we cover through Friday. I will give you a practice exam Wednesday, and it'll be very similar structure as the last one, where there'll be an in-class portion, there'll be an out-class portion. So that's the plan as we move forward. All right? All right.